Semiconductors is a rather large subject. In fact, if for some magical intervention of nature, semiconductors no longer existed, then our civilization as we know it would come to an end. So to talk about semiconductors would take a long, long time. So I've picked out some interesting, well, I find them interesting, perspectives on semiconductors today, and have maybe some...
Can we just check with Mike?
Ah.
Higher.
Oh.
Yeah, try now.
Okay, is that better? Can you hear me at the back?
Yeah.
Good.
Thank you.
Okay. So I was going to say that semiconductors are a rather large subject. So I've just picked out a few aspects of it, which actually may be interesting, but not necessarily blending into a coherent whole. So first of all, let me just say, where are we? Mathematics is regarded as the handmaiden of the sciences. And in some respects, you can say, well, semiconductors are. Because essentially, if you look at the history of semiconductors, it started off really as a branch of both physics and chemistry. The chemistry was actually in the production of large crystals, or particularly of germanium and silicon in the early days, which were relatively defect-free. And these were used for the point contact transistor and the bipolar transistor. And then when the problems of the oxide-silicon interface were solved, then we moved into the MOS transistor and digital electronics as we know it. And this meant actually that the band structure of the semiconductors was largely forgotten about. You assumed it was there, but it didn't matter very much. But these days, we're going back actually to some interesting developments which actually rely upon the band structure and modify the band structure. And some of these I'll be talking about a little bit later on in the talk. So often the question is posed, for information technology as we know it, what comes after silicon? And the answer given by those of us who've worked in silicon and work in silicon is basically more silicon. There are a large number of new materials, new systems coming along, but the notion that you'll be able to make hundreds of billions of transistors, field effect transistors, in such materials with absolute reliability, frankly, does not exist at the moment. Such materials are not present. So it's actually more silicon, more software. But as we see, we know from work in the electronic and electrical engineering department, where we are, that in fact there's a lot of interest and a lot of work in optoelectronics, 3-5 semiconductors, gallium arsenide, indium gallium arsenide, indium arsenide, and so on, but basically for optoelectronics, for high frequencies, and so on. And for non-volatile memories, a lot of work in neuromorphic computing using oxides, high-temperature electronics, diamond, silicon carbide. These are, of course, fascinating areas and very important areas, but insofar as mainstream digital electronics is concerned, essentially, there really is no substitute for silicon and nothing on the horizon. So initially, the technology, the development of the technology needed science. And in fact, does science need the technology? And the answer is totally, uncompromisingly, yes. I had the good fortune to be involved in the discovery of the quantum Hall effect. This came about because we had silicon MOS devices, which were of very high quality, for those days, perfection. And we were able to see the quantized plateaus, quantum Hall effect, and so on. And before that, people had looked at the high field Hall effect in semiconductor devices, in inversion layers, two-dimensional inversion layers. Nothing was seen, really, although with benefit of hindsight, you can see little twitches, which were quantum Hall. But basically, it was because the disorder was too great. And following the discovery, the Bell Labs group, which were developing molecular beam epitaxy, found the fractional quantum Hall effect because they had high-quality materials where no disorder, very little disorder scattering, and so the electron-electron interaction could be seen. Now, it's rather surprising, actually, but the development of silicon chips, for example, these days, devices are approximately maybe 40 angstroms source to drain, 45 angstrom. Although these are called 2 nanometer devices, that is a marketing term which doesn't bear any relationship to the size of it. It's just a marketing term, really. Goes from 4 to 3 to 2. But essentially, that's incredibly sophisticated, hundreds of billions of chips. But how they're contacted together is remarkably crude, actually. You have systems in a package, you have chips, and they're connected by solder. And that is incredibly crude. And what does one do about the heat dissipation? There are hundreds of kilowatts of heat dissipated in data centers. And so what happens in a data center is we have to now develop new methods of conducting the heat away, which is actually, you might have think, almost 19th century. But nevertheless, it actually is a rate-limiting step in the development of the technology. And so one of the interesting examples of terahertz technology is that it can be used actually for investigating the quality of the coupling between successive chips in a systems in the package. So you've got the logic circuitry connected to the memories and so on and so forth. And essentially, TCM, basically, forced liquid cooling requires more innovation to optimize the thermal properties. So Intel have got a superfluid, and this is continuing. However, we need actually to increase perfection in many areas, actually, particularly because quantum physics is, well, there are attempts to morph quantum physics into quantum technology. And there, the electron interaction is extremely important. And if one wants to progress to a true quantum technology, and not just say we're doing quantum physics experiments, quantum requires enormous efforts in actually reducing the disorder element and any imperfections. And that is actually not such an easy thing to do. So here we come back to semiconductor science requiring technological advance. So back to emphasis on band structure. With the discovery of graphene has actually accentuated the search for true 2D materials. And this has given rise to a number of spawning of various tronics. Twistronics, which I will show you in a minute. Valleytronics, in which the valleys of a semiconductor, basically valleys in the conduction band, are used actually as sort of basically as elements in a quantum information system. Straintronics, where we just strain and alter the band structure, and spin orbit, which is becoming quite important actually, in which the internal magnetic field, which depends upon the direction of the momentum, can be used. So higher perfection. And because these systems are basically non-silicon, so there is a lot to be done in actually removing the disorder element and making them better. So the 1980s were really glory years for quantum effects in semiconductor physics, starting with the discovery of the quantum Hall effect in 1980, progressing through to the non-existence of two-dimensional metals, all the way through to instrumentation, the discovery of the STM, the discovery of high TC semiconductors, superconductors, and so on and so forth. And then 1990s, a period of consolidation. But now actually quantum physics of semiconductors and solid state in general is on the move again. And this is an example of twistronics, which was found relying upon the discovery of graphene. Here we have two essentially graphene layers, one on the other, and the top one is rotated by a small angle. And if you can see, I'm not sure, it actually doesn't actually come out very well in this. Can you see? There's a hexagonal band structure imposed upon the system. Basically, you know, the electronic wave function is sort of rapidly oscillating, but imposed upon that is a hexagonal band structure. And so by moving and rotating different angles, one can actually see a variety of effects, ranging from fairly subtle effects of the electron-electron interaction, to basically induce superconductivity. It is quite remarkable how many effects you can see just by modifying the band structure in this way with the twist angle. Now, topological physics started with the formation of the quantum Hall effect, although actually we didn't know it was topological physics. In fact, this whole thing started actually back in the late 1940s with the Kharkov group doing low-temperature physics, in which they essentially injected electrons into a metal, put on a weak magnetic field, and where you come to an edge, you get like that. So the orbits are circular like that, but where you come to the edge, they basically bounce off in a semi-classical way, and you get a current flowing. So here, you get a current flowing at the top, you get a current flowing from left to right. So that goes like that, and that goes like that. In the middle, they are localized, like that. And that's an example of topological current flow. But why is that important? The answer is actually because you can't actually scatter the electrons. The only way you can scatter an electron is actually going from one side to another. And since this can actually be millimeters, it doesn't happen. So you get an electron coming here, there's an impurity, so it bounces like that, it just bounces around it and goes off. It's remarkable how important and useful these classical analogies are. So you get a current which flows, and this current is one-dimensional, and one-dimensionality is essentially quantized, and so you get the quantization of the quantum Hall effect. More recently, you can get the topological insulators, which are basically being utilized as systems for quantum information. And I'll show you why. This is a conventional insulator, you see. You've got electrons going around, in this case an ion, say, no electrons free to move, no conduction band there, valence band there, a gap, and basically nothing in between. This is the quantum Hall we've just discussed here. Edge states there. So now you've got actually, instead of conduction band and valence band, you've got quantized Landau levels. And between them, you've got these states here because there's a continuous distribution. So they just flow in a quantized way. And here you've got the more recent effect of the quantum spin Hall effect, which occurs in a topological insulator where the bands are determined by the spin-orbit interaction. The spin-orbit interaction inverts the valence and the conduction bands and gives one a gap. But at the end of the sample, the situation returns to normal. And so you've actually got states which come down in the gap, much like the quantum Hall effect. And so you can have electrons which flow like that. But there's an interesting difference, of course, because there's nothing like the magnetic field in the quantum Hall to actually confine the electrons. So what you will get is something rather different here. So this is the quantum Hall that we've just discussed. Electron confined round or bouncing round an impurity. But what you get here is the reflection. So if you get actually a reflection, but the interesting thing is that if you take a spin, electron spin, and you rotate it around 180 degrees, the wave function acquires a negative sign. So you now get basically an interference between the electrons going that way, and you get the same effect as in the quantum Hall. You get actually a quantization. So I mentioned the spin-orbit interaction. Why is a spin-orbit interaction? Well, combining the recent developments and fairly older developments as well, the spin-orbit interaction now increasingly understood. Combining that with one dimension and increasing purity, so you get the increasing purity, so you can get essentially ballistic flow and quantization, you can now get an interaction like this. This is what you can get. Now, the interesting thing is, first of all, is that if you've got strong electron interactions in a solid, or in a one-dimensional system, you can actually get basically a breakup of the band structure, and you can get two levels of electrons, two layers of electrons. So go like that, and they split. So you get an interaction which actually causes a line of electrons to split into two to minimize the repulsion. Once you do that, you can actually minimize the electron concentration in one. So this is what you actually end up with. So this is EK relation here, and you split it up into two bands. This is very recent work, last few years. Germanium discovered by Yilmaz Gal, and in gallium arsenide discovered by Sanjeev Kumar, and the theory by Yuval Oreg on the Weizmann Institute. And so what you can have is a situation where these become entangled. This is perhaps, I suppose, one of the strongest entanglement effects known, and which, if you say this band here, minus K plus K, you can now forward scatter, provided the change in momentum is taken up by the reverse scattering of this band here. So basically, the change in momentum has to be identical, positive and negative, and so it's zero. And if you do that, you find that they're entangled, and you start to get a new form of quantization. So it's actually an entanglement-produced quantization, which took us some time to realize, actually. Here, the spin-orbit interaction that I mentioned, which is now increasingly important, it actually corresponds to a magnetic field, the direction of which is proportional and dependent upon the momentum. So it splits here. This is zero. These EK plots here are moved along the axis like that. And now you can get an electrons goes from there to there, scatter from there to there, provided you get here such that the total change in momentum is zero. And this is an umklapp process. I don't go into that at the moment. So just these two. This is actually found in gallium arsenide. This is more germanium. And we seem to have lost the, here we are. So this is what one can get. It's an entanglement-produced quantization. And this can be the basis of new techniques of quantum information. So using quantum physics, it's possible to envisage various applications of these in quantum technology. One's only limited, actually, by the technological achievements of the people who grow the semiconductors and how to get them relatively defect-free. And on that point, I thank you very much for listening.
Yeah.
Interesting talk, Mike, thanks. The process you just described, is how material specific is it? Could it apply to other systems that also have large spin orbit coupling, for example?
Yeah, it's, I mean, you can see it in ultra high quality gallium arsenide with electrons, no spin orbit. Spin orbit material, yeah, very easy, actually. Indium arsenide, this is grown in Santa Barbara, which is very high quality, as you know, which is spectacular, actually, really spectacular. In indium gallium arsenide, yep, and in holes in germanium, yep. So I think actually it's pretty universal, actually. It's just the magnitude of it, as you know, like quantum Hall. So you can get a twitch or a massive effect.